Hey there! Tonight, we're going to explore 50 facts about the universe that sound like they were pulled straight from science fiction, except every single one is real. Some of these facts will make you question reality itself. Others will remind you that the universe is far stranger, far more beautiful, and far more vast than any story we could invent. If you've heard another theory, feel free to share in the comment section. We love discovering new pieces of the story. Do consider tapping or clicking on the thumbs up and subscribe buttons. No pressure, only if your finger feels like doing it. Now settle into comfort, let your mind and body relax, and let's explore tonight's topic together. 1. There are more stars in the observable universe than grains of sand on all of Earth's beaches. Think about that for a moment. Every beach, every coastline, every desert of sand across our entire planet. Now multiply that by roughly 1,000. Astronomers estimate there are about 200 billion trillion stars scattered through the cosmos, a number so vast it defies human comprehension. This estimate comes from deep field images captured by the Hubble Space Telescope and the James Webb Space Telescope, where scientists pointed their instruments at seemingly empty patches of sky and discovered thousands upon thousands of galaxies, each containing billions of stars. When you look up at the night sky and see perhaps a few thousand stars with the naked eye, you're witnessing just the tiniest fraction of what exists. The universe contains approximately 2, followed by 23 zeros worth of stars, each one a sun in its own right, many with their own planetary systems, their own stories of creation and destruction. It's a number that makes our sun seem like a single grain in an infinite cosmic beach. 2. Black holes can ring like a bell when they collide. When two of these gravitational monsters spiral into each other and merge, they don't simply disappear into darkness, they vibrate, sending ripples through the very fabric of space-time itself. These ripples, known as gravitational waves, carry the signature of this cosmic ringing across the universe at the speed of light. According to the LIGO scientific collaboration, which first detected these waves in 2015, the collision creates a series of oscillations as the newly formed black hole settles into its final shape, much like a struck bell resonating with sound waves. Except instead of air molecules vibrating, it's space-time itself that trembles. The frequency of this ringing reveals intimate details about the black hole's mass and spin, allowing scientists to essentially hear the properties of objects so dense that not even light can escape them. Each detection confirms Einstein's predictions from over a century ago and opens an entirely new way of observing the universe, not through light, but through the gravitational symphony of colliding cosmic titans. 3. There's a planet made almost entirely of diamond. 55 Cancri E orbits, so close to its parent star that its surface temperature soars above 2,000 degrees Celsius, hot enough to melt iron. At these extreme conditions, the intense pressure and heat compress the planet's carbon-rich interior into crystalline form. Researchers from Yale University, publishing in the astrophysical journal Letters, determined that this super-Earth likely has a thick layer of diamond beneath its scorched surface. The planet is roughly twice Earth's size but 8 times more massive, creating gravitational forces that squeeze carbon atoms into the precise geometric arrangements that form diamonds. It circles its star. In just 18 hours, meaning a year, there passes faster than a single Earth day. While the surface is far too hostile for any mining expedition, the sheer existence of such a world challenges our understanding of planetary formation. It's a reminder that the universe doesn't just create rocky planets and gas giants, sometimes it forges entire worlds from gemstones. 4. Some stars spin so fast they flatten into oblate shapes. Achernar, a brilliant blue star located about 140 light-years away in the constellation Eridanus, rotates once every 2 days, a blistering pace that causes its equator to bulge outward while its poles flatten dramatically. The European Southern Observatory has measured this deformation, finding that Achernar's equatorial diameter is roughly 50% larger than its polar diameter. Imagine Earth spinning so rapidly that its width at the equator stretched halfway again, as wide as the distance from pole to pole. That's the scale of distortion we're talking about. This extreme rotation results from the star's formation process and creates unusual effects on its surface, including variations in temperature and brightness between the equator and poles. The centrifugal force at the equator becomes so intense it nearly overcomes the star's own gravity, threatening to tear material away into space. It's a delicate balance between gravitational collapse and rotational disruption, played out on a scale almost incomprehensible to human experience. 5. Time moves slower near massive objects like black holes. Einstein's general relativity predicts this phenomenon, called gravitational time dilation, where the intense gravitational field around a black hole literally warps the flow of time itself. Near the event horizon, that point of no return where gravity becomes inescapable, time slows to such an extreme degree that a single minute experienced by someone at that location could equal years, decades, or even centuries for a distant observer watching from afar. NASA's research into Einstein's theory has confirmed this isn't science fiction, but measurable reality. Atomic clocks on satellites orbiting Earth tick slightly faster than identical clocks on the surface, demonstrating time dilation on a small scale. Near a supermassive black hole, this effect amplifies to staggering proportions. If you could somehow survive hovering just outside a black hole's event horizon for what felt like an hour, you might return to find that everyone you knew had aged by lifetimes. Time, that seemingly universal constant, bends and stretches in the presence of extreme gravity like a fabric pulled taut. 6. The cosmic web connects the universe like neural pathways. Galaxies aren't randomly scattered through space but organized along invisible filaments of dark matter that stretch for billions of light years. The Illustris Simulation Project has created stunning visualizations showing how matter arranged itself after the Big Bang, forming a vast network resembling neurons in a brain or blood vessels in a body. These filaments contain most of the universe's normal matter, threaded through enormous voids where almost nothing exists. Where filaments intersect, galaxy clusters form, cosmic cities at the crossroads of the web. The structure emerged from tiny density variations in the early universe, amplified by gravity over billions of years. Gas flows along these filaments toward massive structures, fueling star formation in galaxies. The similarity to biological networks is purely coincidental but striking. Nature seems to create similar patterns across vastly different scales and contexts. Mapping this cosmic web reveals the universe's largest scale structure and helps astronomers understand how galaxies formed and evolved, tracing matter from its nearly uniform distribution after the Big Bang to today's complex arrangement. 7. Neutron stars are so dense that a teaspoon of their material would weigh about 1 billion tons. These compact remnants form when massive stars explode in supernovae, leaving behind cores that collapse under their own gravity to incredible densities. According to NASA's Goddard Space Flight Center, neutron stars pack more mass than our entire sun into a sphere just 12 miles across, roughly the size of a city. The gravitational forces are so extreme that atoms themselves are crushed, forcing protons and electrons to merge into neutrons, creating matter in a state that exists nowhere else in the universe, except possibly in the hearts of black holes. A single sugar cube-sized chunk would outweigh Mount Everest. The surface gravity is 2 billion times stronger than Earth's, meaning if you could somehow stand on one, which you absolutely couldn't survive, you would be instantly flattened to a layer mere atoms thick. These objects spin rapidly, some rotating hundreds of times per second, and possess magnetic fields trillions of times more powerful than Earth's. They represent physics pushed to its absolute limits. 8. The universe might be finite but unbounded, shaped like the surface of a sphere. Stephen Hawking explored this concept in The Universe in a Nutshell, explaining that you could theoretically travel in a perfectly straight line through space and eventually return to your starting point, just as you can walk around Earth's surface without ever reaching an edge. This doesn't mean space wraps around in 3 dimensions the way a planet's surface wraps around in 2. Rather, it suggests that space itself curves back on itself through higher dimensions we cannot directly perceive. There would be no boundary, no wall at the edge of space, yet the total volume would still be finite. It's a mind-bending concept that challenges our intuitive understanding of infinity and boundaries. If true, it means the universe has a specific, calculable size, even though you could never reach an edge. Current observations of the cosmic microwave background radiation suggest the universe is either flat or very close to flat on the largest scales, but the possibility of slight curvature remains open, leaving this profound question unanswered. 9. There's a massive void in space called the Boötes void that's almost 330 million light-years wide. Discovered in 1981 and documented in the Astrophysical Journal, this enormous region of space contains almost no galaxies. While a typical volume of this size might house 2,000 galaxies, the Boötes void contains only about 60, scattered like lonely islands in a vast, dark ocean. It's one of the emptiest regions ever observed, a cosmic desert where matter is inexplicably sparse. The void's existence raises profound questions about how structure formed in the early universe. Some theories suggest it resulted from primordial density fluctuations expanded by cosmic inflation, while others propose it might be the scar of some ancient cosmic event we don't yet understand. When you look at maps of the universe's large-scale structure, you see a cosmic web of galaxy filaments and clusters surrounding huge empty bubbles, and the Boötes void is among the most striking. It's a reminder that the universe isn't uniformly filled with galaxies and stars, but instead resembles a sponge, full of substance in some regions and mysteriously hollow in others. 10. The Andromeda Galaxy is on a collision course with the Milky Way. NASA's observations using the Hubble Space Telescope have confirmed that in approximately 4.5 billion years, these 2 massive spiral galaxies will merge in a cosmic dance lasting billions of years. Despite containing hundreds of billions of stars each, the actual stellar collisions will be remarkably rare. Space between stars is so vast that most will simply pass by each other like ships in an endless night. What will collide spectacularly are the galaxy's enormous clouds of gas and dust, triggering waves of star formation that will light up the merger with brilliant blue newborn stars. The supermassive black holes at each galaxy's center will spiral inward, eventually merging into an even more massive gravitational giant. Astronomers have already nicknamed the result Milkomeda, though by the time it forms, our Sun will have evolved into a red giant, and Earth's fate will already be sealed. The night sky will transform during this merger, filling with new stellar nurseries and altered constellations as the familiar Milky Way band dissolves into something altogether different, a vast elliptical galaxy born from cosmic collision. 11. There are rogue planets drifting through space without a star. These orphan worlds were likely ejected from their solar systems during violent gravitational encounters, flung into the darkness of interstellar space where they wander alone. NASA's Jet Propulsion Laboratory estimates that billions of these nomad planets may exist in our galaxy alone, possibly outnumbering stars themselves. Without a sun to warm them, their surfaces are frozen wastelands with temperatures hovering just above absolute zero. Any atmosphere they once possessed has long since condensed into ice on their surfaces. Yet, deep within their cores, some may retain residual heat from their formation, and a few could even harbor subsurface oceans kept liquid by tidal heating or radioactive decay. These worlds drift through the cosmic void in complete darkness, illuminated only by the faint glow of distant stars. Some may travel for billions of years without ever encountering another gravitational influence. They represent a hidden population of worlds that challenge our solar system-centric view of planetary science. Planets can exist in forms and places we never imagined, untethered from the stars that birthed them. 12. Saturn's moon. Titan has lakes of liquid methane instead of water. NASA's Cassini mission revealed that this strange orange-hued moon, the only moon in our solar system with a substantial atmosphere, experiences a hydrocarbon weather cycle remarkably similar to Earth's water cycle. Methane evaporates from the lakes, forms clouds in the thick nitrogen atmosphere, and rains back down to the surface, carving channels and filling seas. The largest of these methane lakes, Kraken Mare, covers an area larger than the Caspian Sea on Earth. Temperatures on Titan hover around -290 degrees Fahrenheit, cold enough that methane and ethane remain liquid, while water ice becomes as hard as bedrock. The lakes have waves, coastlines, and seasonal variations. Some researchers speculate that life, if it exists on Titan, might be based on liquid methane rather than water, using entirely different chemistry than anything we know. It's a world that mirrors Earth in structure but diverges wildly in composition, offering a glimpse of how alien yet familiar another habitable environment might be. 13. A day on Venus is longer than a year there. This peculiar world takes 243 Earth days to complete one rotation on its axis, yet only 225 Earth days to complete a full orbit around the Sun. NASA's Planetary Science Division has documented this unusual characteristic, which means that if you stood on Venus's surface, somehow surviving the crushing atmospheric pressure and 900-degree heat, you would experience the sun rising in the west, moving incredibly slowly across the sky, and setting in the east. Then, before that single day concluded, Venus would have already traveled more than once around the sun. This backward, sluggish rotation likely resulted from a massive collision early in the planet's history that knocked it into a retrograde spin. The combination of slow rotation and thick atmosphere creates another strange effect. Venus's upper atmosphere actually super-rotates, circling the planet in just 4 Earth days, far faster than the planet itself turns. It's a reminder that planetary dynamics can produce outcomes that seem to violate common sense. 14. Some galaxies have black holes billions of times more massive than our Sun. The largest known, TON 618, has an estimated mass of 66 billion solar masses, a gravitational monster so immense it strains comprehension. Research published in the astrophysical journal Letters indicates that this ultra-massive black hole formed in the early universe when galaxies were actively merging and feeding enormous quantities of matter into their central regions. Its event horizon, the point of no return, stretches roughly 1,300 times the distance from the Sun to Pluto. If you could replace our solar system center with TON 618, its event horizon would extend well beyond Neptune's orbit, swallowing all the inner planets whole. The accretion disk of superheated matter spiraling into this beast shines with the brightness of 140 trillion suns, making it one of the most luminous objects ever observed. Such supermassive black holes challenge our understanding of how quickly these objects can grow. In cosmic terms, TON 618 achieved its staggering mass relatively quickly, suggesting that the early universe had mechanisms for rapid black hole growth that we're only beginning to understand. 15. Light from distant galaxies shows us the universe's past. When astronomers observe a galaxy 10 billion light-years away, they're not seeing it as it exists today. They're witnessing it as it appeared 10 billion years ago, when the light now reaching our telescopes first began its journey across space. The Hubble Space Telescope and James Webb Space Telescope have captured images of galaxies so distant that we see them as they were when the universe was just a few 100 million years old, shortly after the first stars ignited. This means our observations of the cosmos are essentially a time machine, with nearer objects showing more recent history and farther ones revealing increasingly ancient eras. Every direction we look presents a different epoch of cosmic evolution. The galaxies we observe in the deep field images may have long since evolved, merged with others, or even ceased to exist. We cannot know their present state because that information won't reach us for billions of years. Astronomy is, in essence, archaeology. We study the preserved light from ancient cosmic events to piece together the universe's history. 16. Some planets orbit backward compared to their star's rotation. This rare retrograde orbit defies traditional models of planetary formation, which predict planets should orbit in the same direction as their star spins, since both form from the same rotating disk of gas and dust. NASA's Exoplanet Archive documents several hot Jupiters, massive planets orbiting extremely close to their stars, that somehow ended up with retrograde orbits. The leading explanation involves gravitational interactions with other planets or passing stars that altered the orbital plane over time, essentially flipping it. These encounters can tilt a planet's orbit until it moves opposite to the star's rotation. Alternatively, some retrograde planets might have migrated inward from the outer system while exchanging angular momentum with other bodies. The discovery of retrograde orbits revealed that planetary system architecture can be far more chaotic than our relatively orderly solar system suggested. What forms as a neat, co-rotating system can be scrambled by gravitational dynamics into configurations we never predicted, with planets ending up in places and on trajectories that seem to violate the rules of formation. 17. The observable universe is expanding faster than scientists expected. This acceleration, first discovered in 1998 through observations of distant supernovae, completely surprised astronomers who had assumed gravity should be slowing the expansion down. Instead, some mysterious force, now called dark energy, appears to be pushing space itself apart at an increasing rate. According to the European Space Agency's Planck mission, dark energy constitutes about 68% of the total energy content of the universe, yet we have no idea what it actually is. It doesn't emit light, doesn't interact with matter in any way we can directly detect, yet its influence dominates the cosmos on the largest scales. Recent measurements have revealed another puzzle. Different methods of calculating the expansion rate produce different results, a discrepancy that suggests either measurement errors or potentially new physics we haven't yet discovered. This accelerating expansion means that billions of years from now, distant galaxies will recede beyond our cosmic horizon, disappearing from view forever as space between us stretches faster than light can travel through it. The universe is not just expanding, it's accelerating into an increasingly lonely future. 18. There's a star system where it rains molten glass sideways. HD 189733b, a cobalt blue exoplanet located about 63 light-years away, experiences some of the most extreme weather conditions ever observed. NASA's Hubble observations revealed that winds on this planet reach over 5,000 miles per hour, roughly 7 times the speed of sound, and these howling gales hurl shards of silicate glass horizontally through the atmosphere. The planet orbits so close to its star that temperatures soar above 1,800 degrees Fahrenheit, hot enough to vaporize silicate particles that then condense into tiny glass fragments high in the atmosphere. As these microscopic shards fall, the supersonic winds catch them and whip them sideways in a deadly, glittering storm. The planet's deep blue color, reminiscent of Earth from space, comes not from water, but from this silicate haze scattering light in specific wavelengths. It's a world of stunning visual beauty that would be instantly lethal to any visitor, where rain doesn't fall but flies, and what should be solid ground is nowhere to be found beneath the tempest. 19. The coldest known place in the universe is the Boomerang Nebula. Located about 5,000 light-years away in the constellation Centaurus, this ghostly cloud of gas expelled from a dying star registers just 1 degree Kelvin above absolute zero. That's negative 458 degrees Fahrenheit. The European Southern Observatory has studied this nebula extensively, finding it even colder than the faint cosmic microwave background radiation that permeates all of space at 2.7 Kelvin. How does something in space get colder than the ambient temperature of the universe itself? The answer lies in the rapid expansion of gas as the dying star ejects its outer layers. As the gas expands at speeds exceeding 370,000 miles per hour, it cools dramatically through a thermodynamic process similar to how compressed air cools when released from a spray can. This makes the Boomerang Nebula a natural refrigerator of cosmic proportions, achieving temperatures in interstellar space that scientists can barely replicate in laboratories. It demonstrates that even in the depths of space, physical processes can create conditions more extreme than the baseline temperature of the cosmos. 20. You can't stand on Jupiter. This gas giant has no solid surface to support you. If you attempted to descend into the planet, you would pass through increasingly dense layers of hydrogen and helium gas that gradually transition into metallic hydrogen under crushing pressure. NASA's Planetary Science Division explains that Jupiter's surface is arbitrarily defined as the point where atmospheric pressure equals that of Earth at sea level, but there's no ground beneath. As you descended, the temperature would climb to tens of thousands of degrees, while pressure mounted to millions of times Earth's atmosphere. You would be simultaneously crushed, roasted, and eventually vaporized long before reaching anything solid. Some theories suggest Jupiter may have a rocky core deep at its center, perhaps 10 to 20 times Earth's mass, but even this remains uncertain and utterly inaccessible. The planet is essentially an enormous ball of gas compressed by its own gravity into something resembling a star that never quite gathered enough mass to ignite fusion. Standing on Jupiter is as impossible as standing on a cloud. You would simply sink until the conditions destroyed you. 21. When stars die in supernova explosions, they briefly outshine entire galaxies. These cataclysmic detonations release as much energy in just a few seconds as our sun will emit over its entire 10 billion-year lifetime. NASA's Chandra X-ray Observatory has documented supernovae that momentarily outshine the combined light of hundreds of billions of stars. The explosion occurs when a massive star exhausts its nuclear fuel and its core collapses in a fraction of a second, then rebounds in a shockwave that tears the star apart. Temperatures in the blast reach billions of degrees, synthesizing heavy elements like gold, platinum, and uranium that couldn't form in normal stellar fusion. These elements scatter into space, eventually becoming part of new star systems and planets. Every atom of gold in your jewelry, every atom of iron in your blood was forged in such an explosion billions of years ago. The light from some historical supernova was bright enough to see during daytime. On Earth, Chinese astronomers recorded one in 1054 that remained visible for weeks. These stellar deaths are simultaneously destructive and creative, ending one generation of stars while seeding space with the materials for the next. 22. There are entire galaxies made mostly of dark matter. Dragonfly 44, discovered in 2016 by researchers using the Keck Observatory in Hawaii, has roughly the same mass as our Milky Way, but emits almost no visible light. Yale University astronomers found that 99.99% of its mass consists of dark matter, that mysterious, invisible substance that doesn't interact with light but exerts gravitational influence. The galaxy contains only a tiny population of stars, making it appear as a ghostly smudge against the cosmic background. Its existence challenges theories about galaxy formation because we don't fully understand how such a dark matter-dominated structure could form and remain stable. Most galaxies have a ratio of about 5 parts dark matter to 1 part normal matter, but Dragonfly 44 pushes this to unprecedented extremes. The few stars it does contain move at velocities that reveal the immense gravitational field holding them in place. Invisible scaffolding made of something we cannot see or directly detect. It's like discovering a building where the walls and floors are made of material that passes through all our instruments, known only by the way it affects everything inside. 23. The universe's background hum can still be detected today. The cosmic microwave background radiation fills all of space like a faint afterglow of the Big Bang itself. NASA's COBE, WMAP, and Planck missions have mapped this radiation in exquisite detail, revealing subtle temperature variations that are essentially baby pictures of the universe at just 380,000 years old. Before this time, the cosmos was so hot and dense that photons couldn't travel freely. They constantly scattered off electrons in an opaque fog of plasma. Once the universe cooled enough for atoms to form, light suddenly streamed freely through space, and that ancient light has been traveling ever since, stretched by cosmic expansion into microwave wavelengths. When you see static on an old analog television with no signal, about 1% of that visual noise comes from this primordial radiation. It's the oldest light in existence, carrying information about the universe's initial conditions, composition, and geometry. By studying tiny fluctuations in this background glow, scientists can reconstruct cosmic history and test theories about how everything began. 24. Pulsars are cosmic lighthouses that emit beams of radiation with millisecond precision. These rapidly rotating neutron stars sweep beams of radio waves across space like a lighthouse beacon. And when Earth happens to lie in the path of that beam, we detect regular pulses with clockwork accuracy. The National Radio Astronomy Observatory has identified pulsars so regular that astronomers use them to keep time more accurately than atomic clocks. The fastest known pulsars spin over 700 times per second. Imagine a star more massive than our sun, compressed to the size of a city, rotating faster than a kitchen blender. The magnetic fields around these objects are trillions of times stronger than Earth's, channeling particles at the poles and accelerating them to nearly light speed, which generates the observed radiation beams. Their reliability makes them nature's most precise timekeepers. Scientists have even proposed using networks of millisecond pulsars as a galaxy-scale gravitational wave detector, watching for tiny timing variations caused by passing ripples in spacetime. These stellar remnants transform catastrophic collapse into precise, eternal rhythm. 25. Galaxies can cannibalize smaller ones. The Milky Way is currently consuming several dwarf galaxies, including the Sagittarius Dwarf Elliptical Galaxy, slowly tearing them apart with tidal forces over hundreds of millions of years. The European Space Agency's Gaia mission has mapped streams of stars stripped from these smaller galaxies, creating ghostly rivers of stars flowing through our galaxy's halo. This galactic cannibalism is a normal part of cosmic evolution. Large galaxies grow by absorbing smaller neighbors, adding their stars and gas to the larger system. The process is generally non-violent for individual stars because space between them is so vast that actual collisions are rare. Instead, gravity gently redistributes stellar populations over immense timescales. Evidence of ancient mergers can be found in the Milky Way's structure. Certain star clusters and stellar streams bear the chemical signatures of galaxies consumed billions of years ago. Our galaxy's history is written in these archaeological clues, revealing that the Milky Way we see today is actually the amalgamation of countless smaller galaxies that merged over cosmic time. 26. Some comets have two tails, one made of dust, one of ions. The European Space Agency's Rosetta mission observed this dual-tail structure up close, revealing how different materials respond to solar radiation. The dust tail forms when sunlight pressure pushes microscopic particles away from the comet's nucleus, creating a curved tail that follows the comet's orbital path. Meanwhile, the ion tail forms when solar wind, a stream of charged particles from the sun, ionizes gas molecules escaping from the comet's surface and sweeps them directly away from the sun in a straight line. The two tails often point in different directions because they respond to different forces. The dust tail can be white or yellowish, reflecting sunlight, while the ion tail glows blue from fluorescent emission as ionized gas atoms recombine with electrons. During perihelion, when the comet passes closest to the sun, both tails can stretch for millions of miles, creating spectacular displays visible from Earth. The tails always point away from the sun regardless of the comet's direction of travel, so comets actually move tail first when departing the inner solar system. 27. Neptune's winds are the fastest in the solar system. They can reach speeds up to 500 miles per hour, faster than the speed of sound in Earth's atmosphere and powerful enough to rip through steel if such a material were exposed to them. NASA's Voyager 2 spacecraft detected these supersonic winds when it flew past Neptune in 1989, revealing a planet far more meteorologically active than scientists expected at such a distance from the Sun. Neptune receives only a tiny fraction of the sunlight that Earth does, yet somehow generates enormous internal heat that drives these ferocious atmospheric currents. The mechanism isn't fully understood, but it likely involves heat left over from the planet's formation, plus some contribution from gravitational compression. The fastest winds occur in Neptune's upper atmosphere and blow in the opposite direction to the planet's rotation, creating shear forces that spawn massive storm systems. The Great Dark Spot, a storm system comparable in size to Earth, was observed racing around the planet at incredible speeds. It's a reminder that planetary weather systems can achieve violence that makes Earth's most powerful hurricanes seem gentle by comparison. 28. Some exoplanets orbit their stars in mere hours. Kepler 78b, discovered by the Harvard-Smithsonian Center for Astrophysics, completes an entire orbit every 8.5 hours, meaning its year is shorter than a typical Earth workday. This small, rocky planet orbits so close to its star that it experiences temperatures above 4,000 degrees Fahrenheit, hot enough to melt iron and vaporize rock. The planet likely has a molten surface or exists as a partially vaporized ball of rock and metal. Tidal forces at this proximity are immense, gradually slowing the planet's rotation until one side permanently faces the star while the other remains in eternal darkness. The physics of such extreme orbits challenges our understanding of planetary formation because planets shouldn't be able to form that close to stars. The environment during stellar birth would vaporize any nearby material. Scientists theorize that Kepler 78b formed farther out and migrated inward through interactions with the protoplanetary disk or gravitational encounters with other planets. Its existence suggests that planetary systems can undergo dramatic rearrangements, producing configurations we never anticipated. 29. The Milky Way and Andromeda are already interacting through their halos. While the visible galactic disks remain millions of light-years apart, NASA and Hubble observations reveal that the diffuse outer regions of gas surrounding each galaxy, their extended halos, have begun to collide. These enormous clouds of hot, low-density gas extend far beyond the visible boundaries of each galaxy, and where they meet, they create turbulence and shock waves that heat the gas to millions of degrees. This preliminary collision is like the first breath of wind before a storm arrives. The interaction won't significantly affect either galaxy's structure for billions of years, but it represents the beginning stages of their eventual merger. By studying these early interactions, astronomers learn how galaxy mergers progress through multiple phases over cosmological timescales. The collision also reveals information about the composition and extent of galactic halos, which contain significant amounts of mass that's difficult to observe directly. It's cosmic foreshadowing, a glimpse of the first contact between two galactic giants whose full collision will reshape this entire region of space. 30. Space isn't completely silent. Though sound waves can't travel through the vacuum of space because there's no medium to carry them, astronomers have found ways to translate electromagnetic vibrations, plasma waves, and radio emissions into audible sound. NASA's Voyager missions recorded eerie whistles, pops, and hums from the charged particle environment around planets and in interstellar space. These recordings capture radio emissions created by lightning in planetary atmospheres, interactions between solar wind and magnetic fields, and even the boundary region where our sun's influence meets interstellar space. The sounds are genuinely otherworldly, crackling, whooshing tones that seem almost organic, as if space itself were breathing. Jupiter's magnetosphere produces sounds reminiscent of whale songs or electronic music. Saturn's rings create ghostly whistles. These translations aren't arbitrary. They're faithful representations of actual oscillations and waves occurring in space, just shifted from electromagnetic frequencies into the range human ears can perceive. It's a way of experiencing the cosmos through a different sense, revealing that space, while silent in the traditional sense, is filled with electromagnetic symphony. 31. There's a gigantic cloud in the Milky Way made mostly of alcohol. Sagittarius B2, a massive molecular cloud near the center of our galaxy, contains enough ethyl alcohol to make 400 trillion pints of beer. The Max Planck Institute for Radio Astronomy identified this enormous reservoir, located about 26,000 light-years from Earth, along with other organic molecules like vinyl alcohol and methyl formate. These complex molecules form when simpler compounds react on the surfaces of dust grains floating through space. The cloud isn't beer, of course. It's an incredibly diffuse mixture of alcohol molecules and other gases spread across a region hundreds of light-years wide. The density is so low that you could pass through it without noticing. But the sheer volume means the total amount of alcohol is staggering. The presence of such organic molecules in interstellar space suggests that the basic building blocks of life are common throughout the universe, forming naturally, through simple chemistry rather than requiring biological processes. It's both amusing and profound. Space contains the ingredients for cosmic cocktails and possibly the precursors to life itself. 32. The Moon is slowly drifting away from Earth. NASA's Lunar Laser Ranging experiments, which bounce lasers off reflectors placed on the Moon by Apollo astronauts, have measured that our natural satellite recedes about 1.5 inches each year. This gradual drift results from tidal interactions between Earth and Moon. The same tidal forces that cause ocean tides also transfer angular momentum from Earth's rotation to the Moon's orbit. As Earth's rotation slows by a tiny fraction each year, the Moon spirals outward to conserve the system's total angular momentum. This process has been occurring since the Moon formed 4.5 billion years ago from debris of a massive collision. Early in Earth's history, the Moon was much closer, appearing enormous in the sky and causing far more extreme tides. In about 600 million years, the Moon will be far enough away that total solar eclipses will no longer occur. The Moon will appear too small to completely cover the Sun's disk. Eventually, billions of years from now, the Moon will reach a stable distance where tidal locking makes both bodies always show the same face to each other. 33. One day, the night sky will look completely different. In about 100,000 years, the familiar constellations will distort beyond recognition as stars drift through the galaxy at different velocities. The European Space Agency's Gaia mission has precisely measured the motions of over 1 billion stars, revealing that each follows its own orbital path around the galactic center. Stars that appear close together in our sky might be vastly different distances from Earth and moving in completely different directions. Over millennia, these individual motions accumulate, causing the patterns we've known throughout human history to slowly transform. The Big Dipper will stretch and bend, Orion will lose its distinctive shape, and the Southern Cross will dissolve into random points of light. This stellar drift is invisible on human timescales, but inevitable over cosmic time. It reminds us that the constellations, those patterns ancient cultures used for navigation and storytelling, are temporary configurations, meaningful only to observers in specific epochs. Future humans, if they look up at the night sky, will see entirely different patterns and create their own mythologies around stars whose relationships to each other have fundamentally changed. 34. A teaspoon of space dust falls to Earth every second. Over time, this constant cosmic drizzle adds up to roughly 40,000 tons of extraterrestrial material per year. NASA's Cosmic Dust Laboratory has studied these microscopic particles, remnants of comets and asteroids that burn up in Earth's atmosphere. Most are smaller than grains of sand, vaporizing as meteors high above the surface, but their atoms settle gradually through the atmosphere and eventually reach the ground. Some particles are large enough to survive the descent intact, recovered as micrometeorites from Antarctic ice or deep-sea sediments. These tiny fragments carry information about the early solar system, preserving pristine material from the disk of dust and gas that surrounded the young sun. By analyzing their composition, scientists learn about conditions during planetary formation. You've probably breathed in atoms from these space particles, and they're constantly accumulating in soil, oceans, and even on rooftops. Earth isn't isolated from space, it exists within a constant rain of cosmic material that has been falling since the planet formed. 35. If you fell into a black hole, time would appear to stop for you, at least from an outside perspective. NASA's Astrophysics Division explains that due to extreme gravitational time dilation predicted by Einstein's relativity, an observer watching you fall would see your descent slow asymptotically as you approached the event horizon. You would appear to freeze at the boundary, your image growing dimmer and redder as light struggled to escape the intense gravity. But from your perspective, time would continue normally. You would pass through the event horizon and continue falling toward the singularity without noticing anything particularly special at that boundary. The difference in perceived time between you and the outside observer becomes infinite at the horizon. If you could somehow survive and signal back, your transmissions would become increasingly stretched in time until they effectively ceased from the external viewpoint. This strange asymmetry between perspectives reveals how deeply gravity warps not just space, but the flow of time itself, creating situations where two observers can witness fundamentally different versions of the same event. 36. Saturn could float in water. Its average density is about 0.687 grams per cubic centimeter, lower than water's density of 1.0. Meaning it would theoretically float if a bathtub large enough existed. NASA's Saturn fact sheet confirms this peculiar property results from Saturn being composed mostly of hydrogen and helium, the lightest elements, with only a relatively small rocky core buried deep inside. The planet's low density creates interesting structural challenges. The outer layers are gaseous, transitioning gradually into liquid metallic hydrogen under pressure deeper down, with no distinct boundaries between layers. Despite its ethereal density, Saturn's mass is still 95 times Earth's, giving it powerful gravity that shapes its magnificent ring system and family of over 80 moons. The planet's rapid rotation, one Saturn day, lasts just 10.7 hours, causes it to bulge noticeably at the equator, making it visibly oblate even in small telescopes. This combination of low density, rapid spin, and massive size makes Saturn one of the solar system's most distinctive planets. A giant ball of gaslight enough to float, yet powerful enough to hold an entire miniature solar system in its gravitational embrace. 37. There are zombie stars that explode twice. Some white dwarfs, the collapsed cores of dead stars, can survive an initial supernova blast only to reignite years or decades later in a second explosion. Research published in the Astrophysical Journal in 2015 documented these peculiar events, which occur when a white dwarf in a binary system gradually accumulates material from a companion star. When enough matter piles up, thermonuclear fusion ignites on the white dwarf's surface, triggering an explosion. Usually, this completely destroys the star, but occasionally the explosion is weaker, blowing off the accumulated material while leaving the core intact. The white dwarf then continues stealing matter from its companion and eventually explodes again. These recurrent novae can repeat multiple times, creating a cycle of death and rebirth. Each explosion enriches the surrounding space with heavy elements while the zombie star persists, refusing to completely die. It's an unexpected middle ground between stable stars and complete destruction, demonstrating that stellar death isn't always a single definitive event, but can be an extended, repeating process. 38. Galaxies move apart faster than light can travel between them. Because cosmic expansion doesn't move galaxies through space but rather stretches the space between them, this expansion isn't limited by light speed. NASA's Cosmology Division explains that distant galaxies recede from us at speeds exceeding 300,000 kilometers per second, faster than light travels, meaning photons leaving those galaxies right now will never reach Earth. Space itself expands, carrying galaxies along with it, and there's no speed limit on how fast this stretching can occur. Creates what astronomers call the cosmic horizon, a boundary beyond which objects are permanently beyond our view. As the universe ages and expansion accelerates due to dark energy, this horizon gradually encompasses closer and closer galaxies. Eventually, distant galaxy clusters will recede beyond this boundary and disappear from our observable universe, their light stretched to infinite wavelengths by expansion. Future astronomers billions of years hence will see a lonelier cosmos, with only their local galaxy cluster remaining visible, while everything else has raced beyond the cosmic horizon into permanent isolation. 39. You could fit over 1 million Earths inside the Sun. NASA Goddard calculations show that the Sun's volume is approximately 1.3 million times greater than Earth's. Despite being an average-sized star, smaller than many others and larger than many more, its sheer scale dwarfs everything in our planetary neighborhood. The Sun's diameter is about 109 times Earth's, and this dimensional difference cubes when calculating volume. If Earth were a marble, the Sun would be a sphere about 10 feet across. The comparison becomes even more striking when you consider density. The Sun's average density is only about 1/4 that of Earth, because it's made mostly of hydrogen and helium gas, not solid rock and metal. Yet, despite being relatively diffuse, the Sun's mass is 333,000 times Earth's mass due to its enormous volume. The core, where fusion occurs, is much denser than Earth, with pressures and temperatures so extreme that hydrogen atoms fuse into helium, releasing the energy that makes the Sun shine. The scale difference between stars and planets is fundamental to understanding solar systems. 40. There's a planet where it rains iron. WASP-76b, discovered by the European Southern Observatory in 2020, orbits so close to its star that daytime temperatures soar above 4,300 degrees Fahrenheit, hot enough to vaporize metals. The planet is tidally locked, always showing the same face to its star, creating a permanent day side and night side. On the scorching day side, iron vaporizes and gets swept by powerful winds toward the cooler night side, where temperatures drop enough for the iron vapor to condense into liquid droplets. These molten iron drops then fall as rain through the planet's atmosphere in an alien precipitation cycle utterly unlike anything on Earth. The boundary between day and night, called the terminator, becomes a region of transition where you might witness this extraordinary weather phenomenon: clouds of vaporized metal cooling and condensing into metallic rain. Observations show the characteristic spectral signature of iron vapor appearing on the day side but absent on the cooler side, consistent with this rain hypothesis. It's a world where the weather forecast includes showers of molten metal under a star that never moves from its position in the sky. 41. Some black holes shoot out beams of energy brighter than galaxies. These relativistic jets are powered by matter spinning at nearly the speed of light around the event horizon, accelerated by the black hole's rotation and intense magnetic fields. NASA's Chandra Observatory has observed jets stretching for hundreds of thousands of light years, carrying enormous amounts of energy away from the black hole at close to light speed. The material in these jets, mostly electrons and protons, reaches temperatures of billions of degrees and glows across the electromagnetic spectrum from radio waves to gamma rays. The jets form when some of the infalling matter gets channeled along magnetic field lines above and below the black hole's poles, then launched outward in tightly focused beams. These cosmic particle accelerators can influence galaxy formation and evolution across vast distances, heating intergalactic gas and preventing it from cooling and forming new stars. The brightest jets can be detected across the observable universe, making supermassive black holes paradoxically among the most luminous objects in existence despite their reputation for trapping light. They're destruction engines that simultaneously create spectacular displays of energy. 42. The early universe was completely dark for 400 million years. NASA's Cosmic Background Explorer documented this Dark Ages period that occurred after the cosmic microwave background was released but before the first stars formed. Following the Big Bang, the universe rapidly cooled from a dense, hot plasma into a neutral gas of mostly hydrogen and helium. With no stars yet burning, no galaxies yet assembled, space was filled with dark matter and normal matter, but utterly devoid of light beyond the fading glow of the Big Bang itself. This cosmic darkness persisted until gravity slowly pulled matter together into the first massive stars. Objects, possibly hundreds of times more massive than our Sun. When these primordial giants finally ignited, they inaugurated the cosmic dawn, an era when ultraviolet light from the first stellar generation began to ionize the hydrogen gas that filled space. These pioneer stars lived fast and died young, exploding as supernovae and seeding space with the first heavy elements. That long darkness was broken gradually, region by region, as light spread through the cosmos like dawn breaking across a planet. 43. A single pulsar can emit more energy than our Sun produces in a year, in just 1 second. The National Radio Astronomy Observatory has measured these intense bursts from rapidly spinning neutron stars whose magnetic fields are trillions of times stronger than Earth's. These fields channel charged particles at the magnetic poles, accelerating them to nearly light speed and creating powerful beams of radiation. When the pulsar's rotation sweeps these beams across Earth, we detect regular pulses like a cosmic lighthouse. The energy output isn't distributed evenly, but concentrated in these beams, making the total power output staggering. Some pulsars, called magnetars, possess even more extreme magnetic fields. the strongest in the known universe, and can release sudden bursts of energy that briefly outshine everything except supernovae and gamma-ray bursts. During these flares, the magnetar's magnetic field undergoes a starquake, a sudden rearrangement that releases enormous energy. The power comes from the pulsar's rotational energy. It's slowly spinning down, converting angular momentum into electromagnetic radiation, a process that will continue for millions of years. 44. The center of the Milky Way smells like raspberries and rum. The Max Planck Institute for Radio Astronomy discovered that the molecular cloud, Sagittarius B2, located near our galaxy's core, contains large amounts of ethyl formate, the compound that gives raspberries their distinct flavor and contributes to rum's aroma. This bizarre cosmic coincidence occurs because complex organic molecules form naturally in space when simpler molecules react on dust grain surfaces or in gas phase chemistry. Ethyl formate is just one of many organic compounds floating through interstellar space, part of a complex chemical inventory that includes alcohols, sugars, amino acids, and other prebiotic molecules. The fact that our galaxy's center region contains compounds identical to those in familiar flavors demonstrates that organic chemistry is a universal process, not unique to Earth. These molecules don't exist in concentrations you could smell, space is far too diffuse, but if you could somehow gather and concentrate the material, the aroma would be unmistakably fruity and slightly alcoholic. It's a reminder that the building blocks of life and the chemicals we find pleasant or useful are produced naturally by the cosmos. 45. The most powerful explosion ever observed wasn't a supernova, it was a hypernova. These cataclysmic events, first documented in Nature Journal in 1998, can release 100 times more energy than typical supernovae, occurring when extremely massive stars collapse into black holes. The distinction lies in the star's mass and rotation. Hypernovae result from stars at least 25 to 30 times the Sun's mass that also spin rapidly. When such a star's core collapses, it forms a black hole so quickly that not all the outer material has time to fall in. The black hole's rotation and the infalling matter create an accretion disk that generates powerful magnetic fields, which then channel some material into relativistic jets that punch through the star's outer layers. These jets carry tremendous energy, and when they break through the surface, they produce the characteristic hypernova signature, an exceptionally bright explosion with a unique spectral signature. Some hypernovae are associated with gamma-ray bursts, the most energetic electromagnetic events known. The discovery of hypernovae expanded our understanding of stellar death, revealing that nature has mechanisms for explosions even more extreme than the already catastrophic supernovae. 46. A photon can exist in two places at once. Quantum experiments like the famous double-slit experiment prove that light behaves as both particle and wave, defying classical logic and human intuition. When individual photons pass through two slits, they somehow interfere with themselves, creating a wave pattern on the screen beyond. This happens even when photons are sent one at a time. Each single photon must pass through both slits simultaneously to create the interference pattern. But if you observe which slit the photon goes through, the interference pattern disappears and the photon behaves like a simple particle. The act of observation fundamentally changes the phenomenon, suggesting that reality at quantum scales exists in a superposition of possibilities until measured. This wave-particle duality underlies quantum mechanics and has been confirmed in countless experiments throughout the 20th and 21st centuries. It challenges our everyday understanding of how objects should behave. Things should be in one place, not multiple places simultaneously. Yet at microscopic scales, this is exactly how nature operates, following rules completely divorced from our macroscopic experience. 47. The Milky Way has already died and been reborn. Astronomers using data from the European Space Agency's Gaia mission discovered evidence that an ancient version of our galaxy collapsed and regenerated after merging with another large galaxy about 10 billion years ago. This collision disrupted the young Milky Way's structure, causing its gas to collapse toward the center, where it ignited a massive burst of star formation. The merger scattered the original stellar population into a more chaotic arrangement, while the new generation of stars formed what would become the current galactic disk. This death and rebirth event fundamentally transformed our galaxy's structure and composition. The discovery came from analyzing the chemical compositions and orbits of stars. Those born before the merger have different properties than younger stars formed afterward. It's like archaeological layers in the stellar population, preserving a record of this ancient catastrophe. The Milky Way we observe today is the phoenix that rose from that cosmic collision, a second-generation galaxy built from the ruins of its earlier incarnation. And in several billion years, when Andromeda arrives, the cycle may repeat. 48. Some stars orbit black holes at incredible speeds. S2, a star near Sagittarius A. The supermassive black hole at our galaxy's center completes an elliptical orbit every 16 years, at speeds reaching approximately 3% of light speed at closest approach. The Max Planck Institute for Extraterrestrial Physics has tracked this star's motion for decades, using its orbit to precisely measure the black hole's mass and test Einstein's general relativity under extreme conditions. At its closest point, S2 approaches within about 17 light hours of the event horizon, closer than any other observed star. The velocities involved are staggering. At periapsis, closest approach, S2 travels at roughly 5,000 miles per second. These observations have confirmed relativistic effects, including gravitational redshift, where the star's light loses energy, climbing out of the intense gravitational well. Watching these stars provides one of the most direct ways to study black holes, since we can observe their gravitational influence on nearby objects, even though we cannot see the black holes themselves. Each orbit offers new data about space-time structure near these extreme objects. 49. Dark matter makes up about 27% of the universe, yet we've never directly detected it. It doesn't emit, absorb, or reflect light, making it invisible to telescopes, but its gravitational influence is undeniable. NASA and ESA observations show that galaxies rotate too fast. The visible matter alone doesn't provide enough gravity to hold them together at their observed rotation speeds. Something invisible must be providing additional gravitational pull. Galaxy clusters bend light from background objects more than their visible mass would allow, again suggesting unseen matter. Computer simulations of cosmic structure formation only match observations when dark matter is included. Despite decades of searching using increasingly sensitive detectors, we haven't identified what dark matter actually is. Leading candidates include weakly interacting massive particles, WIMPs, or axions, hypothetical particles that interact only through gravity and possibly the weak nuclear force. The inability to detect dark matter directly remains one of physics's most frustrating mysteries. We know it's there. We can map its distribution, we can measure its effects, but we cannot identify what it's made of. 50. Dark energy is even stranger. It pushes the universe apart. This mysterious force, discovered in 1998 through observations of distant supernovae, is believed to make up nearly 70% of everything in the cosmos, yet we have no idea what it is. The discovery earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of the universe's fate. Unlike normal matter and dark matter, which exert gravitational attraction, dark energy seems to exert a kind of negative pressure or repulsive force that acts uniformly throughout space. As space expands, dark energy's density remains constant. More space means more dark energy, causing the expansion rate to accelerate over time. This acceleration means the universe won't eventually stop expanding and collapse back on itself. Instead, it will expand faster and faster forever, ultimately scattering galaxies beyond each other's cosmic horizons. The nature of dark energy remains one of physics' greatest unsolved problems. It might be Einstein's cosmological constant. It might be a dynamic field that changes over time, or it might point to modifications needed in general relativity itself. Whatever it is, dark energy dominates the universe's dynamics on the largest scales. And there you have it, 50 facts about the universe that sound like science fiction but are entirely real. The universe doesn't need embellishment. Reality itself offers wonders that challenge our imagination and push the boundaries of what we thought possible. If you enjoyed this exploration through cosmic facts, please give this video a like and subscribe to the channel for more content that celebrates the remarkable universe we're part of. Drop a comment below with your favorite fact from today's list, or let me know what cosmic topic you'd love to see. Which fact made you pause and think? Which one will you share with someone else? Thank you so much for joining me on this journey. I'll see you in the next video.